So, hello everyone. I would like first to thank the organizer for giving me the opportunity to present this research from my hotel room. So today I'm going to talk about dust evolution in photo-dominated regions, so works that have been done in close collaboration with Nathalie Izard, Emilia Barr, Anthony Jones, Laurent Verstraat, and Anna Bergel. So dust is involved into many environments in the universe through star-forming regions, protoplanetary disk, and so on through different processes such as the gazetting through the photoelectric effect, formation of molecule on grain surface, and the efficiency of these processes strongly depends on the dust properties such as the size, composition, and shape. This is why we need to understand and constrain those properties in order to understand better interstellar dust and therefore understand better the different environments where dust is involved. The problem is that in the universe, there is a wide disparity in the physical conditions that triggers an evolution of the dust properties through phenomena such as accretion, coagulation, fragmentation, photodestruction, and so on. So one of the main objectives of this work was to understand how interstellar dust evolves as a response to the physical conditions. And to this purpose, we're looking into regions where the physical conditions are strongly contrasted and are spatially resolved. And these regions are photo-dominated regions. So if you zoom inside galaxies, you will find molecular cloud close to energetic stars that emit a lot of energetic photons that are going to penetrate inside the molecular cloud and therefore dissociate molecules. But beyond a given depth inside the molecular cloud, there won't be enough energetic photon to dissociate molecules because those photons have either been used to dissociate molecule or been absorbed by a dust grain. And this is the end of the photo-dominated region and the beginning of the molecular region. And if you zoom inside those regions, you will find that the physical conditions are varying on many orders of magnitude on very small spatial scales. And this is why PDRs are a unique place to study dust evolution as a response to the physical condition. So in this work, we studied 3 different photo-dominated regions that are the Orsets in here at 3.6 micron, IC63, and the Oyomba. We have access to 10 photometric bands from 3.6 microns to 500 microns, covering the whole dust electromagnetic emission spectrum. So to model dust emission, we use the interstellar dust model THEMIS together with the dust code, which allows us to model dust emission in optically thin regions. But as PDRs are optically thick, we needed to perform radiative transfer, and to this purpose, we use the 3D radiative transfer code SOC. So regarding the THEMIS dust model for the diffuse interstellar medium, you can find here the size distribution of this model and here the associated spectra. So basically, you have a power law size distribution of carbon-aqueous nanograin that are mostly emitting in the near and mid-infrared and which are responsible for the aromatic and aliphatic bands. And you have 2 log normal size distribution of large silicateous grain and large carbon-aqueous grains that are mostly emitting in the far infrared. So in order to fit the observation, we have to tune the THEMIS dust model for the diffuse interstellar medium, and we especially tune the nanograin size distribution. And to this purpose, we modified 3 parameters, and I'm not going to show you the influence of variation in these 3 parameters on the dust emission in the optically thin limit. So the first parameter we vary is the nanograin abundance. And on the left, you have the size distributions, and on the right, you have the associated spectra. So basically, what you see here is when you increase the nanograin abundance, you increase the dust emission in the near infrared, but also in the mid-infrared, and the emission in the far infrared is very affected, which is normal because nanograin are mostly emitting in the near and mid-infrared. So if you have more nanograin, you will have more emission in the near and mid-infrared. The second parameter we vary is the nanogram size from 0.4 nanometer in blue to 0.9 nanometer here in red. So what you can see is when you increase this parameter, you lose emission in the near infrared, you gain emission in the mid infrared, and you barely affect the emission in the far infrared, which is normal because when you increase the nanogram minimum size, you redistribute the dust mass from the smallest nanograin that are responsible for the near-infrared emission to the largest nanograins that are responsible for the mid-infrared emission. And you barely touch the large grain, so you barely affect the emission in the far infrared. And finally, the third parameter vary is the nanograin power exponent from alpha, from -7 here in blue to -4 here in red. And what you see is when you increase this parameter, you lose emission in the near infrared, you gain emission in the mid infrared, but you also gain some emission in the far infrared. So this is normal because when you increase this parameter, you lose the smallest nanograins that are responsible for the near infrared emission. You gain some of the largest nanograins that are responsible for the mid infrared emission, and you gain some of the large grains that are responsible for the far infrared emission. So this was to give you a clue of what is going to happen when we're going to now proceed to radiative transfer in the optically thick limit. So then what we did is we apply radiative transfer to those three PDRs, and we define a chi-square that quantifies the difference between the dust observed and the dust model emission. And we minimized this chi-square for those three PDRs in the free space defined by the nanograin abundance, nanograin minimum size, and a nanograin power law exponent. So here you have an example of the chi-square distribution in the 2D space defined by the nanograin abundance and the nanograin minimum size for a given value of alpha. And what you see here is that we have a clear minimum for IC63, and it is the same for IC6, and this is the same for the Orsed, and almost the same for the Orion bar. And here for the Orion bar, you have an image of the final results. So basically what you have here is 5 different subplots which correspond to 5 different photometric bands. In green, you have the dust observed emission across the Orion bar, and in blue, you have dust model emission, and you see that we reproduce pretty well the emission. And finally, we obtain a set of parameters, so nanograin abundance, minimum size, and alpha for the 3 PDRs. And instead of looking at what's number, what you can keep in mind here is the nanograin abundance is lower than in the diffuse interstellar medium, and that it strongly varies from one PDR to another. For instance, there is a factor 10 of difference between the Orsed and the Orion bar, and we're going to explain qualitatively and quantitatively this difference later. And the also other important result is that the nanograin minimum size increases by a factor 2 from the diffuse interstellar medium to those PDRs, and that it barely varies from one PDR to another. So now, in order to understand this variation in the nanograin abundance from one PDR to another, we're going to focus on the mechanisms that are at the origin of the formation and the destruction of the nanograins. So regarding the formation of the nanograin, we propose a scenario where the aggregates are pushed towards the denser part of the PDR due to the radiative pressure induced by the illuminating stars. And therefore, this is going to lead to collision, and those collisions are going to trigger fragmentation of these aggregates into smaller grain and therefore into nanograins. And to assess whether it is a viable scenario or not, we need to be sure that the collision velocity is larger than 1 meter per second, because conversely, it will lead to the stinking instead of the fragmentation. And also, we need to be sure that the collision have time to happen. In other words, we need to be sure that the collision timescales are lower than the typical time during which dust grains are processed in PDRs, which is the advection timescales, and which is of the order of 10 to the power 3 to 10 to the power 4 years for those PDRs. So we use a classical 1D approach and solve the equation of motion of a dust aggregate, which says A. So you have the equation of motion with the radiative pressure force, the drag force due to the collision with the gas, and the gravitational force. And the asymptotic solution of this equation provides you with the velocity drift. And from this velocity drift, you can define the collision timescale between an aggregate which says A1 and another which says A2. So here is represented the velocity drift for the three different PDR as a function of the dust size. And here you have the collision timescale between a dust aggregate which says A with another aggregate which says A0, which correspond to the most abundant aggregates. So the first thing is the velocity drift is always larger than 1 meter per second. So fragmentation, so the collisions lead to the fragmentation. Second thing is the collision time scales are always lower than the typical than the advection time scale. So the collision have time to happen. So collision have time to happen, and collision lead to the fragmentation. So this is a viable scenario to explain the nanograin formation in a PDR. And the other thing we can say here is that the collision fragmentation time scale is most likely proportional to the collision time scale. And based on that, if we look at this figure, you see that the collision time scale is almost the same for the Ørsted and the IC63, meaning that the nanograin formation efficiency must be roughly the same, but that in the Orion bar, it is at least 10 times lower than in the Ørsted, meaning that the nanograin formation efficiency must be larger in the Orion bar than in the Ørsted. But we're going to come back on that later. Regarding the nanograin destruction, it is more difficult to establish timescales because there are different mechanisms that can explain the destruction of nanograin, like direct photodissociation, photothermal dissociation, Coulombic explosion, and others. So what we did is we compute two quantities that are the absorption timescale, which correspond to the time between the absorption of two consecutive photons by a dust grain, and we compute that for the three different PDRs as a function of the dust size. And we also computed the average energy of an absorbed photon by a dust grain for the three different PDR. So basically, the idea is the larger the energy of an absorbed photon is, the most likely you're going to destroy a nanograin. And for the absorption scale, so if you absorb more photon, a dust grain is going to be most likely more photoprocessed and more easily destroyed. So this is how we can compare for one PDR to another with hands, how photodestruction behaves. So here what you can see is, for instance, is that if you compare from the Orion bar to the Ørsted, the energy of an absorbed photon is roughly the same. So if there are differences in the nanograin destruction efficiency, it's most likely because of the absorption time scale. And you see here that in the Orion bar, you absorb at least 100 times more photon than in the Ørsted. So most likely, the photodestruction is more efficient in the Orion bar than in the Ørsted. And as I said a bit before, we're now going to explain the difference of a factor 10 in the nanograin abundance from the Ørsted to the Orion bar. So to remind you, from the observation, we found that there are at least 10 times less nanograin in the Orion bar than in the Ørsted. So from this figure, so now we're going to focus on the destruction of the nanograin. So here you see that the average energy of a photon absorbed by a dust grain is almost the same in the Ørsted and in the Orion bar, which means that if there are differences in the nanograin destruction efficiency, it depends on the absorption time scale only. And you see here that from the Ørsted to the Orion bar, you lose, there is a decrease by a factor 100 of the absorption time scale, which means that the nanograin destruction efficiency is almost 100 times larger in the Orion bar than in the Ørsted. And if you now look at the formation of the nanograin, you see that the collision time scale is decreased by a factor 10 from the Ørsted to the Orion bar, which means that the nanograin formation efficiency is 10 times larger in the Orion bar than in the Ørsted. And if you combine those two results, it means that the ratio between the destruction and the formation is 10 times larger in the Orion bar than in the Ørsted. which is in accordance with what we found from the observations. So to summarize, we propose a scenario where the aggregates are pushed towards the denser part of the PDS because of the radiative pressure induced by the illuminating star, and it's going to lead to collision between aggregates, and which is going to lead to fragmentation into smaller grain and therefore nanograins. Those nanograins are then unshielded and unprotected from the radiation field and are easily photoprocessed. And to finish, I think, 15 minutes. Okay. And I'm gonna stop here on this conclusion about the perspective. So there are very beautiful observation that you will think, I think we already saw of the Orion bar, and there will be like other observations of other PDS, for instance, the Orson Nebula. I don't know when, but if you want to know more about that, you can talk to Miriam and Alain. So yeah, I think I'm gonna stop here. So thank you, and I hope you heard me well.